Hello, everyone. Thank you so much for attending the talk. My name is Rajeev Jain, and I work at Argonne National Lab on different computational and data science projects. And I'm very happy to present you our brand new package, UXarray, which is essentially a xarray-styled package that enables standard data analysis techniques on unstructured grids. Before starting, thanking my sponsors or the people who fund the project. SEEDS project funded at DOE, and that's at Argonne and UC Davis. Project Ryzen funded by NSF, and that's at NCAR. So yeah, first SciPy, and excited to be here with you guys. So to begin with, let's see what unstructured meshes are and why there is the need in the community for this package. So understanding it, this slide kind of motivates that. So we have, climate and global weather modeling solutions, and in the past 20 years we've seen like good development in solvers and techniques to go from structured lat-long to variable resolution and to go fine grid on the use of unstructured meshes for Earth simulations. So unstructured meshes typically can be for anything. Like unstructured meshes, it's like for automotive, for everything. Here we're kind of limited to unstructured meshes on a sphere for geoscience track and different kinds of unstructured meshes. So what you see here is cube sphere mesh, latitude longitude mesh, icosahedral mesh, and a regionally defined mesh. On the right you see a completely unstructured mesh. So the requirement for an unstructured mesh is all the elements are sort of connected. There shouldn't be any hanging nodes. All the elements can be of any shape, size, different sizes of polygons. They could be only on ocean, only on land. So yeah, different. It comes with a whole sets of new problems when you're coming from structured world to unstructured world. Here kind of some of the efforts that the E3SM project, the Excelscale project that is coming towards an end now. Lots of national labs and government labs work on this one, and they like many other tools, they have come up with a coupling solution to couple land ice, ocean, atmosphere, river, sea ice models. And some of my colleagues at Argonne, they work with this, and they've demonstrated this to work on Frontier and other big machines. So all these tools sort of have different modes of working, different ways they handle input outputs, and so recognize that there is a big need for a unified tool that handles the post-processing for these components. So that's where it comes in UXarray. So each component has their own things, and you have like different flags after your command line tools, -D, 100, with some lat-longs, and sea ice model was done by somebody else that uses some other command line and everything. So with the whole popularity of xarray, we decided to make UXarray because that was something that was needed, and there's a lot of work that's needed in order to make that happen, because the functions that you want to operate on a structured mesh, they are very different from what you operate on in a structured mesh, and they're very computationally expensive and a lot harder to implement. So there's a lot of algorithms that are needed, and in the current practice, what you typically do is you have unstructured mesh output, so you have an extra step to plot it on structured grid, and then you visualize and do so. You want to kind of eliminate all those. So right from the get-go, we have a very strong foundation, and in like years worth of development, we've made good ground, and so today I'll be presenting some of those results. So our goal is to kind of get an open source library with all the bells and whistles conforming to the standards of the industry, and work with the community. And so that the grid would work with any lat-long grid with partial coverage or full coverage of the sphere. It would be able to interpret different conventions. So right now the industry is very scattered. Everybody has their own conventions. Some use XLS, some is UGrid. UGrid has different conventions, varieties, and there is MPass grid, and yeah, it's a nightmare to work with all those formats. So we want to kind of be able to load in all those and provide geometry and various other operations to work directly on them through this library. So kind of to put it concisely, we need like an extensible library that is scalable, open source, library should have kind of 3 major arms to it: computational operators, some support for plotting using all the current standards that Pangeo has, and a good chunk of development is at NCAR, so they're close to the Pangeo team, and so right from the get-go we are conforming to all the standards there. So then next is the regridding part. So we want to kind of make this all open to the community, and we are getting good community traction from this, like some pull requests already from outside contributors. So we want to kind of make this a project, not just us, but something that can extend and have life after the funding is over for us. So usual suspects here. So all xarray, Jupyter notebooks, GitHub's the center of the universe, some Numba. I'll talk about some Numba results that I had. Task for parallelism, and Pangeo kind of conforming to everything. So the base of the repository, we had a long discussion on how do we start this and what would be our representation of the grid internally. So we decided to take the UGrid conventions, because that has been there for some time. Some projects use it, some don't, but a good chunk of them use. They have some different conventions inside, but we decided to go with that and use that because it's consistent, portable, and sort of extensible too, because you have a bunch of required variables. So like on the right, if you see, you want to specify a CF role mesh topology that has to be there specifically. If that's not, then you just fail. You have a topology, dimension, node, coordinate space, connectivity, and then there are optional attributes. And we can add our own attributes for when we do different algorithms to make it more extensible. So the design overall is sort of, we are inheriting from xarray, and so we inherit and get a UX data set, UX data array, because that's like very familiar with what xarray does. So you're in a very familiar realm of using all the xarray operations when you inherit from xarray. Although it's discouraged, we had a long discussion, and in fact, in a year's worth of time, we did a whole redesign of the package too. So the current design we have is we inherit from xarray and make UX data set and UX data array to work on things. Currently, we have support for loading, writing UGrid, MPass script, and Exodus. And we are actively working on other operations. So as far as the computational operators, we have integration, area calculation, and some other operations for geometry and intersection that are under the works and should be available soon. Some plotting is available and regridding is available. Looking at a sample code, it's just like xarray, you import a UXarray, open the data set, then you can call in specific functions to calculate area or to integrate. And now here the caveat is that you could load in different data variables. So let's say you have a mesh and you have temperature, pressure, or different variables in different files. So you can load them all together. I'll go over on the Jupyter notebook to go over that to see to show you how that is all done. And then you can only open the grid file and look at the grid to understand what all the grid has. So for the MPass support, we have support for both primal and dual meshes, and that's kind of the visualization that was done. So how that all is done and everything, it's all thoroughly documented. I'll go over that again also, skipping that here because I want to go over in a notebook, examples notebook that we have. So these are some of the results that I did for area calculation. So area calculation is an important step that we do. So you have your Gauss-Legendre quadrature points and order. So you can compute area with different quadrature rules and orders. So here we just use triangular quadrature, 4th order, and then compute area on ocean mesh. And these are all different resolutions, a different number of faces. So 1700 faces to like 3.5 million faces and over that. So with and without Numba, the performance gain is like 60x. This was like on a regular laptop, the regular Windows laptop, i5 processor, 8 gigs of RAM. So the largest file is like roughly around 11 gig. So still everything on a laptop, but we kind of see that here we really need that. And the initial points, like for the smaller ones, we've already seen it in the Numba tutorials and all others, that you have some time there to actually compile it. So the first times, maybe the speed up is not that much. But afterwards, as you go forward and you get bigger meshes, that initial compilation time and the time to create that object file is not very large. It's very small compared to the gains that you get. So another analysis is the error analysis, sort of, to see how much time you want to spend calculating and what order you want to use. Although it highly depends on what kind of elements you have, if your mesh has bad elements, or if your mesh, the quality of the elements and how much precision you need. So like this one was for a 3.5 meg file, which had around 3.5 million elements. The mesh can be downloaded from here, and you have two different quadrature rules, Gaussian and triangular. For Gaussian quadrature, you have order from 1 to 10 that you could use to calculate the area. For triangular, you could use order of 1, 4, 8, 10, 12. You could use higher orders too, but that's what I tried here, and I'm kind of trying to show that. So for all different quadrature rules and orders that you see on the table here, the calculation time is the total time it took to calculate the area of the sphere. That's all. It's a simple calculation. And then you measure the error, because we know the area is like 4 pi, and then you measure the percentage error. So for the first quadrature rule, there is some higher error, but after that, the error is consistently in the order of -8. So you could easily use, so by default for the code, we set it to triangular and 4, but you could use whatever. We're lucky that this was a good quality mesh, so it's consistent throughout. But if you have elements that are a mesh that is very finely refined, or some elements that are too big, you'd get much different percentage errors. So some more visualization work that has been done. So the representation of the mesh is all in UGrid construct. So you can represent things in vector geometry. So like if you see here, the vector geometry here is like the entire representation is in polygons. So polygons, lines, and those construct. On the right that you see is the rasterized geometry. So that has all pixels. So there's support for these types of visualization, and underneath everything is the UGrid convention that we use to visualize. In here, we just represent the ocean mesh, again with nodes and with the MPass mesh dataset on the side. We do Conda releases every month. There's active development, bug fixes, changes, and new functionality that's being built. So with that, I think I want to go to the notebooks and our example documentation, sort of. So our community page and the documentation, read the docs page, is fully populated with all the documentation of the classes and the user API and the internal API. So we would love for you to take a look at this, find bugs, report, or even just use the tool and report things on our GitHub page. So there's a nice development pipeline also that we have. So starting with the first notebook, which is sort of working with unstructured grids, going over the conventions and going over the things that we just had. So the notebooks kind of describe in detail our methodology and how we do things, what all has been implemented. So here we import UXarray, load a mesh file, and load in 3 different variables, v1, v2, and v3. So we just use ux.openDataset. You give it a grid path, but you only load in the first data variable, that is v1.nc. Yeah. Yeah. That good? Yeah, so you have your mesh file as grid.nc, and there are 3 data variables, v1, v2, and v3. So you load the mesh files. You load the mesh file and a data file with open dataset, and you essentially get a UX dataset object which has the coordinates and the data variable here, and everything as you see in an xarray mesh. And if you have extra, I think that will come later on. So then you can also load all the variables, v1, v2, v3 in one call with open MF dataset, again borrowed from xarray. For the topology and querying the topology, we're just checking here if they are the same. I'm kind of glancing over these. These are sort of lengthy. So I'll go over them quickly, but giving you the central idea of how this how these operations work well. So you can query in and get the number of nodes and number of faces and get the topology. Then you can also query in the data variables to see what the dims are or how many number of variables are. So going over, and this one is like if you have a new variable, let's say. So here we are adding a new data array. So say you are saying I want to add a data foo to the grid. Then you could do that by just adding the data. Here I'm just adding some random numbers. So those random numbers, you just assign it to a grid and create that as a data object. And then when you see here, then you can see that that new variable is assigned, and that new variable shows up right next to v1. So only v1 was loaded initially. Now you can load in another variable. So imagine a case where you have another file or you have variable from somewhere else, so you can load that variable here too. Okay. So this notebook is more on the topology of understanding how the topology is set up for the UXarray object. So here I load in an MPass mesh, and on the MPass mesh there is a UX dataset object that is constructed, and we load in a mesh file that is a UGrid mesh file, and NC, that's the netcdf file. So there are different files, but internally everything gets converted into the UGrid file format. So then as you load in the mesh, you can see the grid object. There's a UX grid object. So the UX grid object shows you the grid dimensions, the coordinate variables, the connectivity. So these are all preserved. And you also have, so let's say your initial mesh has all other attributes. So you can look at other parsed attributes. So we store them as parsed attributes. So they're all also available to you. So we do some translation because you have some other convention in the initial file, or there's no convention, like Exodus has some other convention. In fact, Exodus has Cartesian coordinates in its mesh, the initial mesh. In UXarray, we assume that the mesh, the initial mesh that you load in, has construct with the grid construct, mesh to node x, node y. Those are latlons and not Cartesian coordinates. If you want Cartesian coordinates, those are given by mesh to cart x and cart y. So then you can get Cartesian coordinates also. So that's like we're enforcing a standard here, sort of. So extending the whole UXarray object and making life easier for us, because different formats have different requirements, and they're differently. You have to make some line that, okay, I'm going to allow only this, and these are going to be strictly enforced, saying that's how it's always going to be. So that's internal representation still. When you go from one format to the other, we have encode as functions. We don't implement a write function. So you can also write files to Exodus or script or netcdf, different formats, and then you can use still the xarray to netcdf to write files in those formats. So we just encode it in that format, and then the other writing part is still taken care of by xarray. So here, I think there is so you can call in, so we have a property face areas. So you can, in your UX object that you generate, you can call in face areas and get area of individual faces or all the faces, or call in integrate operation to integrate over one or several fields. So I think that's about the topology. I think I want to go to working with MPass grids. So for MPass grids, it's a little different because the same grid has dual and primal mesh. So primal and dual mesh is like you have the primal mesh, which is polygons, and the dual mesh is you take the centroids and create the triangular mesh on top of that. So similar fashion, you work with MPass grids like UXarray.openDataset, but what you specify here is another parameter called useDual. So if you set use dual to false, then it's the primal mesh. Otherwise, it's the dual mesh. And the other constructs of implementing the topology, they remain the same. So this is kind of described in detail on these, and this is on our read the docs page. With that, I think we can compute the areas here, get the area sphere 4pi. That shows up here. This is similar to what I showed in my other examples. So you visualize here. This is just a simple poly collection visualized on matplotlib to show this was the primal mesh, the dual mesh, and then these are both meshes combined. With that, I'll give it to Hangyu, who's a graduate student at UC Davis. And she is working on implementing grid and geometry operations for UXarray.
Thank you, everyone. I'm just going to quickly go over our proposed workflow pipeline for all the operators that we support. So the pipeline will be very simple. Give us your input mesh soup. No matter how messy it will be, it can be concave, it can be convex. We can clean up all your input data, triangulate them so that we can make sure all the data we are going to process will be a convex phase. And after that, we will build a topology building for you. You don't need to worry about any topology on your side. We are going to take care from that. And after that, for each phase, by calling each operator, we can automatically generate the bounding box for each phase on the unit sphere. And then we also provide the function that you can use to calculate the cross-section, basically the intersection between two gray circle arcs or a gray circle arcs and a constant latitude line. And with this cross-section function, we can achieve our ultimate goal called regridding. The goal of that is that you have a first mesh look like triangles, and you have your second mesh looks like squares. And you want to transfer your data from the first mesh to the second mesh, while you want to preserve every information you have precisely. And with our regridding function, we can achieve that for you. Give me your input first mesh and your target mesh. And we are going to internally do all those calculations, transforming, regridding, remapping. And at the end, I'm going to hand out a perfect output mesh that already have the information transfer precisely and exact. And the good part about that is because we use the exact computation paradigm, you can keep switching between mesh without loss of information. Like you can just keep transforming from one mesh to another mesh and transform it back. All your information will be still the same at the beginning. To achieve all those functionality I mentioned before, we're going to propose all these geometry operators. The first one is the Electron box, basically building the bounding box for you for every phase. And then the second one is called cross-section. It allows you to calculate any intersection point on the unit sphere. And then the dual is primarily designed for the M-pass, but it can also be broadened out to other mesh operations. And then after we have those geometry operators, we can achieve all these integral operators. For example, if you want to know the temperature of a certain latitude line, we can give you that non-conservative zonal average for you precisely. And if you want to know the temperature the average temperature between the 30-degree latitude and the 45-degree latitude, yes, we can still give that to you precisely. At the end, if you want to transfer your information from your input mesh to your output mesh, different topology, we can still achieve that precisely and cleanly. A very simple visualization can be viewed here at the graph below. The first graph gives you the conservative zonal average. Basically, there's a stripe of latitude line, and you want to know the average temperature or any other information you are interested. We can write the script, run all those analysis for you, and you just type in, get the zonal average of between latitude 30 to 45, voila, you have a number. And we can guarantee it's precise into the floating point precision. And yeah, that's all.
All right, at this point, we'll open up for questions. So a reminder, anyone online, please go ahead and post those within the Slack channel, the track Ocean Geo, yeah, that one. So does anyone in the room have questions?
So because you inherited from xarray, can you, like, what operations came over with that? Can you do means and, or like, are there certain things you can do and can't do according to?
No, everything came over. Everything came over. We do mean, averages, whatever xarray supports, we support. The only thing is now you have a UGrid object associated. So sometimes some of the functionality didn't work, so we have to inherit that too. But there are a couple of internal functions that needed to be populated also inside of our design in order for the whole design to work. So we added that, and after that, pretty much most of the functionality works. So xarray itself internally, they discourage inheriting from xarray if you want to build a new package. So there is a lot of blah xarray. And the next talk is YT xarray. So they usually in their design discourage it. So we had a good discussion with them, and they are planning to support this, and we had chats with them, and they said it's okay to import, to inherit from xarray. And most of the functionality has come over.
How about subsetting? Can you do that very easily?
Yes. It's working so far, yeah. Maybe with some complicated meshes we might run into something. But everybody's very active on the project. If you post something, an issue or something that you come across, I think in 24 hours you'd have a response.
Any other questions in the room? Got a couple back here.
Thank you. That was a really great presentation. Thanks very much, Rajeev. Twofold question for you. Hopefully it's got some simple answers. First is, have you experimented with regridding, going from your unstructured grid to, say, traditional that long? What do you use?
Yeah.
Can you tell the audience? And the second question is, are you aware of the PyVista xarray project by Bain Sullivan? He's working on producing like accessors where you can sort of visualize rather than just using Cartply or Matplotlib or Holiday Views or anything like that.
The second part first, I am not aware of that package. And for the first part, that was about
sorry, the first question was about regridding. Have you experimented with regridding, going from your unstructured?
Yeah. We've been doing that. So the issues that we come across, like Hangyu mentioned precision a lot of times in her thing. So what we've encountered is during regridding, like when a line passes through something, then you encounter things where things get haywire very quickly if you don't use a large enough precision. So with regridding, that's where we are spending more time to make it more robust. Maybe using a library that uses higher precision than what NumPy has to offer, so that we are accurate, because those errors, they accumulate very quickly, and you don't get the results that you want. And more so when you're using HPC, you're using it for some reason that you want precise answers, and you want to run on a large number of processors. And at the time of, let's say, post-processing or doing actual work, if you lose all that precision, then it really doesn't make sense. So it's important to kind of think through and implement that design. That's where she's putting in a lot of work. So with regridding, we've had some experience. We've like scratched a couple of algorithms, but we are now back to the anvil, redesigning it and making it more precise. Thanks.
Thank you for the talk. So all the focus here was on the ocean sciences and earth sciences kind of view of things. Is there the ability to use this as well for things that are an unstructured grid, but in 3 dimensions, or like a spherical, non-uniform spherical grid that you might use in 3D simulation of astronomy or something like that? And can you represent things like tetrahedrons and that sort of stuff through this? I think about what Mayavi provides. and VTK provides, and wishing I had things that didn't require that large dependency many times to do things. Does this fit that, or is it really driven and designed for this specific community?
No, this is not designed specifically for that. Although the design central and all the functionality is around the geoscience community, because that's where the whole funding and everything and the project main intention is for.
Absolutely.
But UGrid is agnostic, and what we load is agnostic. Like with Exodus reader writer that I implemented, I could see that I could load in any Exodus mesh that is Cartesian. Convert to lat-long red, it doesn't even care about if it's a spherical or whatever. So we try to not put in that many checks in there. So as long as it's a sphere, you did mention though tetrahedron. Tetrahedron is like a 3D. This is only still 2D. You can have a Z dimension, but tetrahedrons we won't be able to present, or that support isn't there. But as long as it's 2D and on a sphere, I think a lot of it can be used. And if you have like your variables in a third dimension, or let's say, as you go in different heights of atmosphere, you have different numbers, and those things can be represented in the mesh.
Great. It's specifically to spheres.
Yeah.
Got it. Great. Thank you.
Yeah. Calling it UXarray. As soon as you see unstructured grid, and then you go in and see, oh, this is only specific applied to this field. Yeah.
Alrighty. Thanks so much.